Now let's go from 1 dimensions to 3 dimensions. It is not very much difference, as you will see. I go in 3 dimensions from point A to point B, and I now have a force which could be pointing not just along the x direction, but in general in all directions. Now the work that the force is doing in going from A to B is F dot dr. R is the position in 3-dimensional space where the force is at that moment, and dr is a small displacement. So if this is from A to B, then dr here, if you go in this direction, this would be the little vector dr, and here that would be a little vector dr. And the force itself could be like this here, and the force could be like this there. The force can obviously change along this path. So let the force be f of x, x roof, plus f of y, y roof, plus f of z, z roof. I'll move this a up a little, put it here. And let dr, the general notation for vector dr, equals dx, x roof, plus dy, y roof, plus dz, z roof. Cannot be any more general. So the work that this force is doing when it moves from A to B is the integral of this FDR. Let's first take a small displacement over dr, then I get dw, that is simply fx times dx, it's a scalar, because this is a dot product, plus fy dy, plus fz dz. That is a little bit amount of work if the force is displaced over a distance dr. Now I have to do the integral over the entire path to get w from A to B. That's an integral going from A to B. Integral in going from A to B. I don't need this anymore. Integral in going from A to B. Integral in going from A to B. Now we're home free because we already did this. This is a one-dimensional problem, and the one-dimensional problem we already know the outcome. The integral f dx we found that is 1/2 m vb squared minus m va squared, which in this case is obviously the velocity in the x direction, because this is a one-dimensional problem. And the one-dimensional problem indicates that the velocity that I'm dealing with is the component in this direction. So we have that this is 1/2 m v b squared, and this is the x component, minus va squared, and that is the x component. This is also a one-dimensional problem now, except that now I deal with the component, with the y component of the velocity. So I get 1/2 m times vb y squared minus va y squared plus 1/2 m vb z squared minus va z squared. And now we're home free, because what you see here is you see v squared in the x direction, v squared y component, v squared z component, and if you add those three up, you get exactly the square of the velocity. You get the square of the speed. So if you add up these three terms, you get vb squared, I lost my m, let me put my m in there, 1/2 m times vb squared, and here you see ax squared, ay squared, az squared, minus va squared, and you get exactly the same result that you had before, namely that the work done is the difference in kinetic energy. You can always think of these as speeds. Velocity squared is the speed. It's the magnitude squared of the velocity.